Our next paper here is titled Development of Thermal Core for Ice Extraction for ISRU Applications.
Yes, so my name is Hota. I'm an R&D engineer at Advanced Cooling Technologies. It's based in Lancaster, Pennsylvania. So I'll be presenting some of our efforts in the Phase 2 SBIR. It's for developing a thermal management system for lunar ice miners. And a major chunk of it is basically developing the thermal core, which is for extracting ice to sustain various lunar surface activities. Just trying to go forward here. All right, so just a bit of a background on this. So we already know some of the recent missions have already verified aggregates to an average of 5% concentration by mass. So a simple calculation comes up at 600 million tons of water, which is present, which can be extracted to sustain various activities. So on our end, when it comes to developing this thermal management system, we are working towards a ice mining rate of 2.78 kilograms per hour. And this basically comes from a baseline a reference activity where, let's say, water extracted is supposed to help with 10 metric tons of oxygen fuel production. But so we know the climatic conditions on the moon surface is vastly different from that of the Earth's atmosphere. We have very low temperatures and very low pressures. So on the thermal side, when we talk about ice extraction, we are usually looking at sublimating the water ice into vapor. And so for that, the extraction thermal power, you can see is about 3 kilowatts. And for collection, we basically have to recondense the vapor back into ice on the collection side. So we'll have to reject 2.8 kilowatts of power there. So we are working with our collaborators, Honeybee Robotics, in developing this entire thermal management system for volatile extraction and collection. So volatile here in this particular project is basically ice. So here you see with this particular flow process, different thermal management components, which basically will be assembled together for the final test. So we basically have the mechanical pumped fluid loop, single phase in nature. So it basically connects the waste heat source like an MMRTG and delivers heat to one of the main components, which is the thermal corer. And the entire presentation is actually around the thermal corer here. So thermal corer is basically used for ice extraction here. It basically has many channels on the drill auger. And we have a rotary union, which basically facilitates the fluid loop between a stationary component here and a rotating component like the corer. And later on, we'll be developing a VCHP integrated cold trap tank, and that's basically for collecting the volatile ice collection, so to speak. So this is just a schematic representation of how we would envision the entire thermal management system to be on a vehicle here. So we basically have the corers here, power source connected to the battery. So this is our electrical supply, and then we basically have the VCHP radiator panels for heat rejection to the bioradiation, basically. And so for one particular vehicle, we basically have some preliminary calculations, which was done in phase 1, basically. So we're looking at 60 kgs of entire system weight, including the batteries and the power source. 0.33 kilograms per hour of ice mining rate, and then we have this particular thermal and electrical energy demand. So we'll come to the crux of this presentation, which is looking at the thermal corer for ice extraction. So to speak, the thermal corer is an improvement on the PVAX drill. So PVAX drill was the original concept, which was developed by our collaborators, the Honeybee Robotics, for ice extraction. So just for the sake of convention, I'll call PVAX drill as a standard corer here, which is this particular figure. So you have a drill auger with an internal volume, capture volume. So the water ice regolith, which fills this capture volume, is basically heated up, and that's where the sublimation occurs, and the sublimated vapor is captured. So a standard prototype, which was demonstrated, and which we will consider for the sake of this presentation as the state of the art, is about 5 centimeter in ID and 50 centimeters long. And so it has basically 1000 cc of internal capture volume. And so with their experiments, where they actually used a heater blanket for sublimation, and saw up to 65% of ice extraction efficiency. So where our innovation comes into picture is basically integrating mini channels into the standard corer, and we'll call this the thermal corer here. So the thermal corer with mini channels for fluid flow for ice extraction. So we'll have the hot fluid inlet and the cold fluid outlet at the top of the manifold. So the hot fluid coming in basically distributes into four channels, basically separated out, and this basically spirals downwards, the hot fluid, and it converges at the bottom manifold and then flows through the annular space outside and then flows outwards from the top of the manifold again. So here's a schematic, this is basically the thermal corer that was 3D printed. So this one is 5 centimeter ID, but 17 centimeter for the demonstration purposes. Another schematic basically laying out the same, the hot fluid representation in red. So we'll have the hot fluid basically flowing close to the inside captured volume, because we want majority of the heat transfer occurring to the inside of the corer for the sublimation of regolith. And so the hot channels you see basically the channel size increases in aspect ratio as it flows down. And then at the bottom, it finally converges. And then it flows outwards. The cold fluid flows outwards, more closer to the outside of the corer. And then we basically have the cold fluid flowing outwards completely. So some initial analysis, we work on the structure, just to look at the structural integrity of the thermal corer. So we're basically comparing it with the standard corer here, which is the PFAWS drill. So some mechanical loading conditions here, 10 Newton meter of torque, 100 Newtons of vertical force. And this is basically the values we have from our collaborators who basically did some experiments previously. And so with this standard comparison, we actually see the factor of safety is quite similar compared to the standard corer. And this is for the 17 centimeter drill. And so just to look at other longer drills just for parametric sweeping, we basically see even for a 100 centimeter long drill, basically can get a factor of safety greater than 20. So structurally, the thermal corer is stable even with the mini channels, even with the thinner walls we have because of the mini channels. So coming to the main part of the presentation for the ice extraction experiments, which was quite a bit of a challenge. So this is what we treat as a major accomplishment for us. So this is basically a CAD schematic of the entire experimental system we have assembled and for which we are testing ice extraction with the thermal corer. So we have the regolith housing and liquid nitrogen coil wraps around it. So we have the thermal corer, which is placed inside the regolith housing. Here you can see a sectional view of that. And this is actually pre-packed with wet regolith, 5% of water by mass basis. Thermocouples placed strategically to read temperature distribution at various points, and also the pressure transducers to look at the pressures. So the hot fluid flows into the mini channels, heats up the captured regolith inside, and the sublimated vapor will actually flow through this vapor line, flows through the vapor line and is collected in the volatile cold trap tank. And so in the cold trap tank, we basically have liquid nitrogen coils inside it. And this basically serves as a stand-in proxy for the VCHP integrated cold trap tank, which will be the final component will be developing soon. We have a vacuum pump basically because we'll have to maintain very low pressures to simulate the lunar environments. So this is the experimental system we have assembled in-house just before the experiment. So everything's basically insulated, the components. So we have the regolith housing here, vapor line connected to the cold trap tank, and a turbo pump for vacuum. So a couple of sets of experiments we did. We basically are maintaining the initial and the cold wall on the regolith chamber at minus 20 degrees C, and we are pulling down the vacuum to around 70 minus 3 torr. The cold trap tank, we are basically maintaining at a touch lower temperature at minus 50 C just to have that ice deposition happening there. So one set of experiments where we have heat transfer fluid at 50 degrees C. So we are using ethylene glycol 60% volume as the heat transfer fluid. And the reason is basically we don't want the fluid in the residual fluid in the thermal core to freeze when we are basically cooling down the whole system to minus 20 C or below. So in this case, we basically have about 25% of ice extraction. And essentially, if you're looking at the temperature profile here, the temperature plots of interest is your TC4, which is the black line, and TC5, which is basically the dark, thick red line. So this is basically the temperature at the center of the regolith core, the black line, and this is on the inside wall of the thermal core. So we basically see some residual temperature difference maintain constant. So we have good amount of heat transfer occurring initially, and then as the vapor deposition rate decreases or ice extraction rate decreases, we see a shift in the temperature profile. Another aspect that leads to this is basically the drier regolith closer to the wall is actually has lower thermal conductivity compared to the wet regolith. Another simultaneous activity we are also looking at is basically developing numerical models so as to match with the experimental results, and this will basically help us expand into different profiles and different test conditions that we would actually want to develop the final prototype to be. So we are working with 2D axisymmetric models with user-defined functions and answers. So basically have the actual condition here. So the left boundary is basically the actual condition at the center of the regolith core. And then we have the thermal core wall encountered to the right. And then outside is basically the environment. And below is the environment, the expanded feature here. So with the user-defined function, this is basically the solution scheme which we have adopted. And so as the hot fluid flows through the many channels in the thermal core, we basically start increasing the temperature of the regolith, which is captured inside. And so that changes the saturation pressure of the fluid, which basically is water in our case. And that also changes the properties like the specific heat and the thermal conductivity, which is a function of the ice fraction that is available, the temperature, local pressure, porosity, etc. And so we are essentially solving the entire energy and the fluid flow equation from the heat transfer fluid to finally determine what actually is the temperature distribution and ice mass fraction that is left in the captured volume. So the essential difference between initial and the final volume left, final fraction left, will be the amount of ice that is extracted. And other internal calculations will be the specific heat capacity of the regolith and the thermal conductivity of the mixture. So some initial conditions we had with the numerical model, we had mean fluid temperature of 42 degrees C. And that was essentially the average temperature of the fluid going into the thermal core. And a back pressure of 3000 pascals, which is basically the resisting average pressure from the cold trap tank, which we actually observed during the experiments. And so with some experiment, which some parametric fit corresponding to the regolith morphology, porosity, etc., we basically see a decent match when it comes to the temperature profile on the drill wall inside surface and also the center. And here are some snapshots at different instances when it comes to the temperature distribution and the ice mass fraction that is left inside the captured volume. So with the simulation, we have about 50% efficiency, which we observe within 60 minutes. And from the experiments, we have 25%, but basically I'm marking it as star because this was, this was one of the very first experiments we did, and we noted some points where we can actually improve on the experimental side. So another set of experiments which I'm showing here. So this time we have the heat transfer fluid at 75 degrees C. So we have a high temperature growth in the captured volume of interest, and so high extraction efficiency initially and the short-lived transient period and stable period. And after this, we basically see a quick drying out of the regolith nearer the core, near the corer. But with this particular test, we have more than 55% of ice extraction efficiency. And the reason why I say more than 55% is we basically noticed that there is some amount of residual water which we were not able to extract when we were actually putting it on the measuring flask. So we're still figuring out ways to capture the entire volume for a more clearer number. And also the other aspect here is the assumption here is initially when we insert the regolith in the pre-packed sand, we're going with the assumption that the sand flows without any resistance into the thermal corer volume. But again, we basically want to do some simple experiments to see if we are actually filling out the entire volume inside the corer, or if there is a small fraction of space that is still left in the corer. So here's a snapshots of ice deposition that is happening on the cold trap tank. So like I said, we have the liquid nitrogen coils inside the cold trap tank to serve as the proxy for the heat pipe, VCHP heat pipe surfaces. We basically have a side glass on one side and basically allows us to visualize. So which gives us this cool images of ice depositing on surface. What we see is the ice deposition rate is much higher initially, but then the deposition rate decreases as we proceed in time. Again, a multitude of parameters at play here could be depleting ice mass fraction closer to the heat transfer surface, which reduces the thermal conductivity, changing thermophysical properties of the mixture itself. Increasing back pressure, so to speak, from the cold trap tank, and that kind of resists newer vapor depositing inside, etc. So there are different parameters that play here. So just going forward, we are still doing more tests to find what the optimum parameter is for this particular prototype, and then have the numerical model go in handy so that we can actually use the numerical model to find what actually is the more optimum geometry and the optimum operating parameters for ice extraction here. Soon we'll be delving into the VCHP radiator cold trap tank. We already have good experience with the VCHP radiators, and also with the cold trap tank we have good amount of information with this particular test itself with the proxy cold trap tank we had. So we are quite comfortable in finishing this effort quite quickly soon. And then soon we'll be integrating the entire system with a mechanical pump loop design. Also on the numerical side, we'll be basically soon coupling the numerical models for the ice extraction and also the collection model. We are right now developing the ice collection numerical model at this point. And soon we'll be working with the collaborators to basically demonstrate the entire assembly to see the ice extraction and the ice collection performance in the entire system, in the thermal management system. So that brings me to the end of this presentation. Basically acknowledge everyone involved internally from the ACT side, the technical monitor, and also our collaborators. So thank you, and I'll take questions if there are.
There we go. Tough to unmute myself sometimes. Thank you very much. That was really interesting. Yeah, if anyone has questions, once again, feel free to put them in the chat and I can read them out. I was just curious. I don't see any questions right now, but I had one myself just to kick things off. The auger design has like the coring design has the threads on the auger on the outside rather than the inside where you're actually collecting the fluid. Is there a specific reason for that, or did you want to see if you could put some kind of geometry on the inside to maybe transfer heat to the regolith better?
So, are you talking about the mini channels more on the
I mean more
spiral
in the
section?
I mean more in the right hand side picture here. The threads that are making up the auger are on the outside where you're not capturing any of the sublimate water. Whereas on the inside of the thermal core, the walls are smooth, it looks like. Is that right?
Yeah, so inside we basically did not want to tamper with the original design with the PVAX drill, but certainly that can be one form of enhancement we are considering going forward. Another aspect would be having some sort of fin structures because one of our discussions with the technology directorate would be to expand on the diameter to capture more regolith inside. And so there will be an interplay of how much capacitance there is, the length to diameter ratio, and also we are actually looking at those structural changes going forward. You heard about that.
Okay, cool. Excellent. Thank you. We did have another question here. Is there much heat transfer between the hot fluid moving downward and the cold fluid moving upward, or are you able to thermally isolate these fluid paths from one another?
So we did initial rough order calculations to see what actually would be the heat flowing into the captured regolith of interest and outside of the environment, not specifically looking at fluid inlet and outlet within the thermal core itself. So, but again, with these rough order estimations, we actually are estimating more than 80% of the heat that flows into the thermal core for sublimation activities. Yeah. So does that answer the question?
I think so. I mean, it does to me, but I'll let Tom, if he wants to follow up, he can. And we'll.
Yes. If yeah, I mean, I can certainly answer the question if you send it over email. I can talk to the team members and then see what actually the question is and how to answer that.
Sure.
If it's a different question.
Okay. Just we might want to give it a minute here in case someone's typing, but. Okay, I'm not seeing too many other things come in, so I think that'll be it for now. And of course, if you have questions or comments or anything, go ahead and feel free to put them in the chat. I saw in the last session there was some good follow-up if you haven't read the chat. It's an interesting thing to see some of the stuff going on there. Oh, we did have a question here. How does the lunar regolith thermal conductivity affect the process?
Right. So essentially, just if we look at this particular chart image here, so we basically have the heat transfer happening from the. Do you all see the image here, by the way? Slide 7.
Yeah, you're still sharing.
Right. So we basically have the captured volume of the regolith here, and so the heat transfer actually flows from here into the inside. So initially, what we believe could be happening is we have a strong heat transfer happening, which is why we see a higher temperature on the wall, of course, than the center of on the axial side. So So as this portion basically dries out, the drier regolith basically has a poorer thermal conductivity, which could be percolating to poor heat diffusion as we proceed in time. And that is where uh, the thermal conductivity of the regolith comes into picture. But again, the conductivity itself is not, I mean, along with the thermal conductivity, there are other factors which will influence the sublimation rate. Or let's say as the pressure and temperature go above sublimation, above the triple point, that's where we basically have liquid to vapor transition happening. So more amount of heat needs to be put in instead of the sublimation itself because of the latent heat changes there. And we also have the influencing back pressure because there is a resisting force from the cold trap tank because we are actually filling up the volume there for the new incoming vapor, and there the pressure is increasing. So we have all these factors at play here.
Pick up the
Yeah,
chat.
so if they're interested, I guess here's this correlation we have where the thermal conductivity is basically linked to temperature, velocity of the mixture and the regolith itself. And this is taken from the literature.